Hi, I'm Steve Herskovitz. Welcome to this overview of the Relational AI platform. RAI is a KGMS built around fully normalized relational data persisted in blob storage. We call our storage format Graph Normal Form, or GNF. By being fully normalized, Graph Normal Form allows you to have multiple graphs, multiple models, against the same single copy of the data. Data can be loaded into the system in several ways. Bulk loading is appropriate for initial data loads from data warehouses, data lakes, etc. Continuous updates are appropriate for streaming events, capturing changes to data warehouse tables and the like. Your workloads running virtual machines, executing your code against the knowledge graph data in blob storage. Our modeling language is called RHEL, so we refer to these compute resources as RHEL engines. Each workload can be given its own appropriately sized RHEL engine and can run concurrently. Because the compute and storage are separated, RHEL engines can be spun down when finished. You only pay for them while they are running. For example, you might do an initial bulk load for Project A. You'd choose a big engine to get this done as quickly as possible and spin it down when the load was complete. Then you'd spin up a more modest RHEL engine to handle the daily incremental updates for Project A. Meanwhile, your developers can begin bulk loading data for Project B in their own RHEL engine without impacting Project A's continuous data feed. No other graph database provides pay-for-what-you-use consumption billing. At the same time, Project A's various graph analytic workloads can each be running in their own RHEL engines, neither impacting nor being impacted by the data ingestion engines. We recently spoke with a company that is building a news-related business application. They process a variety of news feeds with NLP and continuously add data to a legacy graph database. Their data application uses graph queries to find business relationships and dependencies that might predict the ripple effect of news events, but they limit their graph queries to avoid impacting their continuous data feed. With RAI, these news updates can run in a separate RHEL engine from their data app engine, allowing them to use graph queries that explore the data more deeply for insights for their clients. We've also met a life sciences company that has a large knowledge graph with tens of billions of vertices and relationships in a navigational graph database. There are multiple workloads competing for compute on a single 100-node cluster. The production workload supports tens of thousands of users running continuous dashboards and other standard reports and charts. There are also hundreds of researchers writing ad hoc queries. These researchers may not be expert query writers, and they may not be aware of the statistical shape of the graph. This customer told us he hand optimizes the problematic queries run by his researchers. In this legacy environment, a poorly written research query can severely impact the performance of the production workload. Increasing the number of nodes in the cluster can help somewhat, but does not fully protect the production workload. With RAI, the research workload can run in its own separate, smaller RHEL engine. Our semantic optimizer greatly reduces the need for hand optimization. Semantic optimization is enabled by the relational paradigm and is not possible with navigational technology. Researchers can impact each other, of course, but the performance of the production workload is fully protected. In fact, as the diagram shows, you can have any number of workloads running concurrently. These RHEL engines can be quickly spun up on demand. Divide your users into groups oriented by task or perhaps by billable organization. Each group gets one or more engines sized for their needs that can be spun up and down so the group incurs expense for compute only when it is being used. No other graph database supports separation of workloads in this way. You use our modeling language RHEL to describe the relationships and rules in your business domain. The data you load then populates the model with facts and attributes. Computed knowledge is incrementally updated as new data arrives. Graph analytics algorithms include shortest path, cycle detection, centrality, similarity, and weakly or strongly connected components. The use cases include logistics, deadlock detection, supply chain, recommendation systems, fraud detection, and social network analysis. In RAI, your graph analytic workloads can use sophisticated business logic, including nonlinear recursion and reasoning against the knowledge in the model. Consider, for example, an app designed to prevent customer churn. It uses machine learning to predict customers at risk and reasoning to prescribe the best course of action. In some cases, the customer is too far gone to save. In other cases, the recommendation is to spend resources to make the customer happy. Or consider a credit card user wishing to detect fraud. They want to identify fraud rings and cliques, groups of people who work together to commit fraud. Graph queries generate features that are used by ML algorithms to detect fraud. Or consider the use of counterfactuals to provide explainable AI. We're working with a nonprofit agency to explain credit decisions. When an applicant is denied credit, the graph is searched for similar applicants who were granted credit. The denial is then explained with counterfactuals that say, for example, if you earned $200 more per month or closed 2 of your credit card accounts, your application would have been approved. We'll cover the machine learning workloads in a few moments. RAI supports cloning of databases. A clone copies only metadata that refers to the data in blob storage without copying the data itself. This gives you a second logical version of your knowledge graph identical to the first and requires no extra physical storage. Your dev teams can take advantage of this. Instead of asking for a full copy of production, which might take a long time or be too expensive, a clone of production quickly gives dev a version of the knowledge graph that they can safely modify without fear of impacting any production data or workloads. Any number of such clones might be made available to developers on multiple projects. The first use case protects production data from dev activity. This second use case shows that some workloads instead want to be protected from production activity. If you are doing continuous integration or reporting, you may want stable data, protected from continuous data updates or other activity. As a third use case, clones are useful for longer-term preservation of data, such as for compliance or disaster recovery. In general, clones can replace backups by retaining older data in blob storage. This makes that data immediately available if needed to recover from a bad data update or other disaster. Periodic clones can serve as compliance backups, permitting a new RHEL engine to be spun up with a clone for compliance reporting. Clones might also be used to compare results obtained from a known version of the data using different versions of the RAI software or different versions of your own business workloads. No other graph database combines zero-copy cloning and workload concurrency to give you this type of analytic flexibility. Today, feature engineering is mostly done against data warehouses or data lakes. Some data scientists may also be extracting data from knowledge graphs, but there is otherwise no connection between the graph and the machine learning. That data is extracted into a data frame expected by machine learning packages. In some cases, that data frame might optionally be added to your feature store. In our world, feature engineering involves defining new relations that compute these features from the knowledge in the graph. Essentially, your features become new knowledge added to the graph and incrementally maintained as new events occur. New features can be defined without impacting your existing features. You save money, time, and effort by not having to fully recalculate all your features each time you want to retrain your model. This moves you closer to being able to continuously update your model. Contrast this with the relatively static nature of your feature store. With our integrated machine learning, RAI hosts a collection of classic machine learning packages which run in the cloud alongside your knowledge graph. We currently support MLPack, XGBoost, and GLM, and are working to integrate more. The data scientist uses RHEL to specify the feature relations for this learning task. The system transforms them into a data frame provided to the machine learning algorithms. The resulting trained model is returned as a module in RHEL. With our accelerated machine learning, the algorithms operate directly against the feature relations. No data frame is extracted. This is cutting-edge work being done by our R&D team in collaboration with our research network of professors and graduate students. Together, we are inventing these algorithms and publishing papers about these techniques, then implementing them in RAI. Notice again that machine learning of either type is done in its own RHEL engine. There's no impact on any production workloads. Each RHEL engine can be sized as needed, and you only pay for it while it is running. The bigger the RHEL engine, the faster the training goes. This lets you run more training experiments, and with more iterations, you can be more confident you have found the best model. In summary, RAI combines the best of the cloud architectural features that have become the new standard and the relational features that have repeatedly proven to bring business value with declarative modeling language and reasoning, graph analytics, and machine learning. Looking further ahead as we progress on our journey, you'll begin to ignore the distinction between integrated and accelerated machine learning workloads. Instead, you'll focus on being able to analyze your data with graph, reasoning, and learning in a single platform. Let's discuss some sample workloads.